So it's our honor and pleasure to have Alessandra Buonanno, one of the great pioneers of the prediction of gravitational wave emission. And she's going to tell us about tests of general relativity using current gravitational wave observation. And it'll be 25 minutes plus 5 for questions. Go ahead, Alessandra.
Do you hear me?
Yes.
Okay, so first, thanks for having me here to talk about gravitational waves and tests of general relativity. So let me start with this picture of the gravitational wave spectrum, just to highlight the fact that with LIGO and Virgo today, and also pulsar timing array, and in fact also cosmic microwave background probes, we are probing a small part of this spectrum that extend over many decades of frequency, as you can see here. LIGO and Virgo is probing the 10 Hertz, kilohertz, nanohertz here, and the femtohertz for CMB probes. On the top axis, this is the wavelength, and it's interesting to observe that with the black holes of LIGO and Virgo, we are in fact observing black holes with size of the order of a few hundred kilometers, and here more distances also of the order of parsec. Now, the reason why I'm highlighting this is because different wavelengths, as we will see in a moment, probe black holes of different sizes, from stellar to billion solar masses, but also different wavelengths probe even the same, the black hole with the same mass at different times of their evolution, of their life, interacting with different astrophysical environments. This can be easily understood. This is just an animation that shows 5 of the black holes observed by LIGO and Virgo and the binary neutron star, just using the Kepler law that everybody here knows. The orbital frequency inversely proportional to the orbital separation, and the gravitational wave frequency is just a multiple of the orbital frequency. So the shorter, the more the two black holes come close to each other, the larger will be the frequency. And if you probe different wavelengths with the same, mass, fixed mass, you are looking at different stages of the coalescent process, whether it's the Inspiral, whether it's the Plunge, or the merger, or the final object. Also, the bandwidth decides also which black holes we can see, because the merger more or less happens at this gravitational wave frequency. So you divide by the total mass of the binary. So for million solar mass black holes, LIGO cannot see them because they are merging in the milliards. So the waves bring fingerprints of the source and also the gravity theory. So how do we extract parameters? Well, of course, we use Bayesian analysis, but just to give an idea, from the evolution of the frequency over time, we infer the masses. From the amplitude and the masses, we can infer the distance, the source from the Earth. From the time of arrival, the amplitude and the phase at the detectors, we can reconstruct the location in the sky of the source. And also from the modulations that we can observe in the amplitude and in the phase, we can extract information about whether the black holes were spinning slowly or fastly, and also whether the orbit was eccentric or was circular. And finally, by comparing two waveforms with deviation from general relativity, we can probe gravity, and in particular do null tests of general relativity. We heard yesterday, already in the section of yesterday, talks about the fact that with ground-based and future space-based detector, we are probing the strong, highly dynamic regime of gravity, which is not accessible from the solar system. Also, experiment like gravity and, of course, the Event Horizon Telescope are looking more at stationary black holes and either matter or photons that interact, and then we observe. Binary pulsars, strong field, but still low velocity. One variation of these plots that appear in many talks, I'm showing you here, this is actually the curvature in units of the inverse of kilometers And this is the potential for a single object, but for a bound, like a binary system, this can be treated with the velocity squared divided by the speed of light, the characteristic velocity of the binary. And I show this plot just to highlight the fact that there is complementarity between, for example, ngEHT and gravity and the ground-based detectors in terms of curvature that they are probing. And the box here represent the fact that, as I was saying, we are seeing black holes of different size. And stellar mass black holes are the best to probe curvature, the largest curvature. But LISA is going to see also supermassive black holes. This point here represents Sagittarius A star, and here M87, which is a larger black hole than Sagittarius A star. And I wanted also to point out the fact that the orbital period of the binary changes a function of time. But for LIGO and Virgo sources, its second derivative is actually changing over time, which is not the case for binary pulsar, where p dot is very small, but is basically not changing because the two bodies are very far from each other. And here we are seeing them up to the end. Okay, so just to put this in context, so since the first discovery, LIGO and Virgo have observed 47 more binary black holes and 2 binary neutron stars. You see again here the range in masses in unit of solar mass. There is actually a variety in the mass, and also we will see in the mass ratio of the binary. These are the 2 binary neutron stars that very likely merge into a black hole, although from the data themselves, we couldn't really prove that this remnant was a black hole. Now, using this data, in particular, half of the third run of LIGO and Virgo, 24 binary black holes were used to do tests of general relativity in this paper published by the collaboration. The 24 are listed here. It's not that you have to understand all the numbers here, just the total mass. We extract the final mass of the object, also the spin of the final object. To these 24, 8 binary black holes were added also from the first and second run. And this, by the way, is the signal-to-noise ratio. Several tests were done. These are all null tests. I will only discuss 3 of them, but let me just list them here. So by subtracting the best waveform that match the data, we can do a residual test, understand the correlation in the residual, in the noise after subtracting the signal. Consistency test about the Inspiral, merger, and ring down. I will describe the so-called parametric test of the gravitational wave generation. Spin-induced moment for the first time. This measurement was also done. Test of the propagation of gravitational waves, so-called dispersion relation. Ring down test for the properties of the remnant formed after merger. Echoes that could be there if the surface is not an horizon of the dark object, but a reflective surface. And finally, polarization of the gravitational waves. Now, I wanted to show, before I go into the test, again, I want to highlight the fact on the left, we had also quite special events in this latest run. Events characterized like this one by a large asymmetry between the masses that you can see in these simulations. The signal in this case was quite long. And again, I want to stress the fact that Inspiral, testing GR in Inspiral, merging down, it's all important to test the nature of the dark object. In this case, also the spin of the primary was measured at the level of 0.4, 99% confident level. You see the little spin on the primary black hole here, and these were the masses of the 2 objects. On the right, there is another very important event, the 1905-21, and you see this event was very short, very different. We just saw the last few cycles before merger. So, for example, the kind of tests that you can do in these 2 cases are different. In one case, you focus more on the remnant. In the other case, you can focus on the long Inspiral. Okay, so now let's go to the first test, this parameterized test of the generation of gravitational waves. This relies on the fact that I was saying the orbital period varies very, very quickly at the very end, almost p dot by an order of magnitude between 30 Hz and 130 Hz. So we are very sensitive to the phase of the gravitational wave. In general, you can write the waveform as in frequency domain as an amplitude and the phase. And the phase is written here. In the first part, we have the post-Newtonian expansion in powers of v, which can be traded with the frequency and also depend on the total mass. And because we are very sensitive to the phase, for this test, the amplitude of the waveform was fixed to the GR value, so was not varied. Now, this coefficient here depends on physical effects. Spin-orbit coupling, spin-spin coupling, they are known in post-Newtonian theory up to 3.5 post-Newtonian order, v to the power 7. And they take different values if the black hole is not a black hole in general relativity, if it is in another theory. I want also to stress that this coefficient here, which then are varied, and we do the Bayesian analysis over the 15 parameter of the waveform plus the deviation parameters, depends on the conservative and dissipative part of the dynamics. This is interesting because, for example, with gravity or EHT, one is mainly measuring the conservative part, of the black hole. I mean, you are basically measuring the space-time, the metric, the light ring, etc. So here we intertwine the conservative and dissipative. Why? Because how this phase is computed. It's computed by starting from the binding energy, which is computed in post-Newtonian theory, solving the Einstein equations, the luminosity at infinity, given by leading order, the quadrupole formula. And then we use the balance equation that relates the energy loss to the luminosity at infinity to basically extract the phase, I mean the orbital, this is the first derivative of the orbital phase, and by integrating, we get the gravitational waveform. So this is interesting because if you were doing some comparison with, again, gravity, EHT, etc., you have to keep this in mind because in this other test, you are going just to probe the conservative part of the dynamics. So you would be need to disentangle or to distinguish the conservative and dissipative part in these contributions. So let me discuss the results. So in this plot that shows the posterior distribution after marginalizing on the other parameters for the deviation parameter, this is the dipole emission, and it was also discussed yesterday by Enrico Barause. You can see this is the other post-Newtonian parameters. They all encompass 0, which will be the GR value. But for the merger ring down, I didn't show in the previous transparency, but we have also a parameterized form of the phasing, where now the coefficients are not the post-Newtonian coefficients, are just coefficients that are extracted from numerical relativity simulations of binary black holes. So we can also test them. No deviation from general relativity, we can put at 90%, we can compute the upper bounds at 90% confidence level, which is shown in this lower plot here. Again, the best, not surprisingly, upper bound is for the dipole radiation, because this starts at -1 p.n. order. So it's very effective for a long inspiral. And in fact, the best bound comes from the binary neutron star. But for example, the simulation I was showing, the event I was showing you before, is one of the one that produced actually one of the strongest results for the binary black holes. Now, these other parameters are, it is the leading order, the quadrupole, basically coming from the quadrupole emission, which we could go below 10%. Other parameters are, few of them at the level of 10%. But this is the first time that we are testing these parameters, because as I was saying, in that formula, they are not tested by binary pulsar or other probe, because they combine together dissipative and conservative effects. I want also to highlight or stress, this was also done by Enrico yesterday, we don't use the post-Newtonian expansion in the phasing close to merger. we do something else, as I was explaining, because it's not reliable. Similarly, the post-Newtonian expansion of the dark object metric would not be reliable to test strong field with the Event Horizon Telescope. And this was also discussed in this paper by Enrico Baraus and collaborators, and also yesterday by him. The other test I wanted to discuss is about the quasi-normal modes. Actually, the first bound on the quasi-normal mode of the Remnant was done even in the companion testing GR paper of the discovery of gravitational waves 5 years ago. But in this new paper by LIGO-Virgo, this test was done much more thoroughly and for many events. So as we know, the remnant object of the coalescence of two black holes, we believe is a perturbed Kerr black hole, which relaxes in the stationary Kerr state by emitting quasi-normal modes. And this quasi-normal mode frequency and decay time for astrophysical black hole should depend only on the black hole mass and spin. This conjecture can be disproved if we can measure more than one quasi-normal mode. This is the so-called black hole spectroscopy. At the moment, we don't measure more than one quasi-normal mode because we don't have enough signal-to-noise ratio in the merger ring-down part of the signal, but we can measure at least the dominant quasi-normal mode. And the collaboration used two methods. One is you take an Inspiral merger ring-down waveform and you deform the ring-down quasi-normal modes that are in the signal. You can see an example here if you vary by 10% the frequency and decay time. And the other method is just to use damped sinusoid. So I show you the results of the two-dimensional posterior distribution for 3 of the events that were analyzed. The events were also combined hierarchically because this deviation that we are introducing could be not constant, could depend on the property of the source. So you cannot just multiply the likelihood function, and this is the result. Also for directly, coming from here for the frequency and decay time of the dominant mode. And there have been also results in the paper that use just the damped sinusoid. You can look more into the LIGO-Virgo paper about that. In the last months, because we have been involved in this analysis, we have added more events coming from the third third run of LIGO, and also the first and second events. And so this is a new result, which put together more events. And is summarized also in this plot here. This is for the frequency and decay time, again, of the dominant 2-2 mode. This is the upper bound at 90% credible level. This is by combining just the likelihood, and this is with the hierarchically combined value that you can see. For the frequency, the 10% is basically given by the first event of LIGO. Even the best single event is still the 150914 because it had a signal-to-noise ratio around 8 for the merger ring down. The decay time is less well-bounded, but now I want to emphasize the fact that already from the decay time of the quasi-normal mode, this already strongly hints to a black hole because the decay time is of the order of few milliseconds. And if you take a neutron star and or a boson star even, they have much longer decay times. Moreover, these measurements are already informing us on the nature of the dark object, about the light ring, about the horizon. Yesterday we heard also the talk by Paolo Pani that these results can, for example, say that the surface of the dark object is away from the 2m if it were Schwarzschild by just 1%. This is, for example, one of the impact that a measurement of the frequency of the dominant mode at the level of 10% could have, already has. And another thing I wanted to say that in general relativity, the quasi-normal modes are related, as I was saying, to the light ring and the horizon. There have been some studies to understand whether this can be already used to compare with current results from ngEHT. But as we heard yesterday, but also from paper in the literature, So until now, the light ring of M87 has not yet been observed. So we have to wait for next future measurement to be able to compare these results also with what we are learning from ngEHT. Okay, the last test I want to talk about is the spin-induced quadrupole moment. This is a measure of the object oblateness due to the spin. And if the dark object has this spin-induced quadrupole moment, it is imprinted as many other effects in the gravitational waveform. So in the expansion of the waveform of the phase I was showing you before, this is one of the terms that is there. And the quadrupole for a black hole, the quadrupole can be written in terms of the spin of the object, the spin square, and the mass. And there is a coefficient in front, which is 1 if it is square, in general, if it is a black hole in general relativity, but it ranges between 2 and 14 for neutron stars, then 150 for slowly rotating boson stars. So this is a quantity that for the first time, the collaboration tried to measure. And actually what was measured was a combination of the deviation of this quantity with respect to the Kerr value, which is given by this. And here you see the posterior distributions for some of the events for this quantity, delta kappa S. And when you put together different events, whether you use a joint likelihood or this hierarchical combine, these are the first measurement of this quantity with gravitational wave observations. Are not very tight at the moment, but will improve certainly in the future with more events and larger signal to noise ratio. From that phasing, we can also extract information about the tidal deformability, which should be 0 for black holes, it's not 0 for neutron stars. Tidal heating, the black holes can absorb gravitational waves. Some of the gravitational waves don't go to infinity, but can be absorbed by the holes. And it can increase a little bit the mass and the spin of the object. And this was not actually attempted to be measured, but will be done with higher signal to noise ratios. Okay, so now let me have just 2 slides to say where we are going with the runs.
3 minutes, Alessandra.
3 minutes. Oh, I finished. So the third run ended in March of last year. The fourth run will start not earlier than June 2022. With a range which is the maximum distance at which we can see binary neutron star at this level. Later on in this time frame, the fifth run should take place with better sensitivity because using squeezed light and other improvements will also bring Kagra and hopefully LIGO India. And we will go from several tens to hundreds of binary detection per year. And in fact, for 04, we expect in 1 year 150 events. We are still probing, however, the local universe, even for 04 and 05. The situation, of course, will change for the next decades with a new facility on the ground, which will open and widen the frequency band up to 1 Hertz and also make it deeper around the kilohertz. And of course, ELISA, which will open a new bandwidth around the millihertz. And I want to highlight that ELISA will bring a exquisite test, but also Cosmic Explorer and Einstein telescope of general relativity. And this is the quadrupole moment deviation that ELISA could measure for extreme mass ratio binaries. So this is the same configuration as you are probing of the Sagittarius star or M87. But at this level, these numbers, these labels here are referring just to different population of MRIs and different models for extracting the information. So just to finish, gravitational waves are pristine astronomical messengers. They offer unique opportunity to test gravity. We are lucky that we are not, we don't have a lot of contamination from astrophysical effects as perhaps, with EHT you have. Gravitational wave observations with LIGO and Virgo are already probing strong field gravity, the nature of compact object, and by this I mean multiple moments, like ring of horizon is all imprinted in the waveform and can be unveiled at each stage of the coalescent process, whether it's the Inspiral, where the two component dark objects are, the merger or the ring down. I show you at least 3 of the null tests that have been done. In the future, if Inspiral merger in down waveform in modified theory of general relativity will be available, specific tests can be done, not just parameterized tests. So future is very bright. We will have many more sources with much higher signal to noise ratio. And I think there will be unique synergies between different experiments in the future with gravitational wave detectors, with gravity, ngEHT, and I look forward also to the next generation of Event Horizon telescopes. Thank you, and I finish, I hope, in time.
You finished on the minute.
Thank you.
And thank you for a fantastic talk on fantastic science. And I see that Aditya has a question.
Yeah, so my question is regarding the transfer of tools that we can have from, let's say, the studies of LIGO to the study of EHT. So one of the things that the ngEHT wants to measure accurately is the mass and spin of the black hole, right? Now, in LIGO, there are 2 avenues being explored here. One is the so-called mass gap in the gravitational wave events, and second is encoding mass in the QNMs. So QNMs is a little skeptical because the current correspondence it has an error bar of 30% or whatever. But my broader question is, do you see any tools that can be transferred from, let's say, studying the mass and spin of the black holes from LIGO to measuring the mass and spin in the ngEHT? Relativity tools, that is. Thank you.
Yeah. So, yeah, this is a good question. Of course, with gravitational waves, the way in which we measure the masses is mainly from actually the best estimation of the masses come from, as I was saying, the evolution of the phase over time. And this is a dissipative effect. This is something that you don't have with ngEHT. So, I mean, I think the best way to measure the spin is certainly from, the matter, the innermost stable circular orbit, from, which people use already. So if you want, by using the effect, the strong field effect on the matter. Now, your question is more about using the photons, perhaps, directly. The light ring, of course, give you information also about the mass and the spin, because the light ring position does depend on the mass on the spin. But you have to observe the light ring, and we discussed yesterday, this is challenging. What about the innermost stable circular orbit? Is that something that can be extracted?
I think the EHT people will answer that better.
Yeah, I think it's actually quite difficult because the pressure support from magnetic fields and just thermal pressure is significant. So it's not a clean measurement like in other systems. I don't know if Charles or Ramesh or any of the simulators want to comment more on whether there's any hope of identifying clear orbital signatures that could be tied to just properties of the space-time, or whether it's always going to be model dependent.
But from strong field effects on the matter, and also the photons, not necessarily close to the light ring, but far, because maybe you cannot have that, but between the light ring and the ISCO, some strong field effect on the matter and and the photons. Perhaps from there you can extract information, because that will be unique of being Kerr and not something else. But even forget about testing general relativity. If your question is just about assuming that it's Kerr, I have to think, but this is the only thing at the moment I can think about.
Could you?
So I was going to respond to that exact point. as soon as we throw variability into the mix, a lot of things become possible that are otherwise very difficult. And so one of the things that we've done, Paul Tita's written a very nice paper on this, is shown that if you have localized emission regions, even if those are shearing out as you might anticipate in a differentially rotating flow, and even if the flow velocity is very non-Keplerian, you can still do this lensing experiment where you are referencing the secondary images to the primary, even in a moderately optically thick accreting environment, and back out exquisite space-time constraints. And you can do this then for, from spots that are launched or for localized emission regions throughout the accretion flow, and you're really just limited by how likely you are to generate one of these spots at large distances. And so in that sense, I think, Alessandra, we could do kind of what you are suggesting, which is probe something about the lensing signal as a function of distance in the accretion flow, and back out some information about the region between the photon orbit and well, not necessarily the ISCO, but in fact all the way out to wherever we have emission.
Yeah, that seems interesting.
We're a minute over, but I'm going to call on Shep, who's had his hand up.
Well, actually, I think Avery made the basic point. I would just say that one of the things that fascinates me about the ngEHT is that we can use the frequency range and look for achromatic signatures and tease away some of the messy astrophysics from the clean GR. And I think that has a lot of promise. And what we'll do tomorrow, if I can just advertise a bit for tomorrow, is brainstorm about what the science observables and questions will be, and then worry a little bit later about the analysis methods, like how we're going to tease those out. So I think there's great promise in both those areas.